Today in science class, we're going to take a look at and review what we learned in Chapter 10, Motion and Momentum. We took a look at in Lesson 1, what is motion? Then we learned a little bit about acceleration in Lesson 2, and then all about momentum and inertia in Lesson 3. Let's begin. Part A, our vocabulary review. The directions tell us to write the terms that are defined below on the lines provided. I'll read the definition, and we're looking to fill in the term that matches that definition. Number 1. When objects collide, the total initial momentum equals the total final momentum. That would be the law of conservation of momentum. Basically dictates when something collides, the energy that is going into that collision based on inertia, an object's ability to resist movement, and momentum, the object's ability to move based on its mass, goes together to give you the total momentum after the initial momentum. So based on what object is moving and how fast it's moving, we'll tell you what that final momentum will be after that collision has taken place. We looked at this with 3 different examples. The larger marble hitting the smaller marble and moving them in the same direction. A smaller marble hitting a larger marble and bouncing off in the opposite direction, and 2 marbles of the same size hitting each other and bouncing in equal and opposite directions basically explains this law of conservation of momentum. Number 2, the tendency of an object to resist change in its motion. The object resisting change based on its mass is inertia. Something that is really big, huge, and heavy, like a train, has a lot of inertia because it takes a ton of energy to get it moving. It's not very easy for you to move. Number 3, the rate of change of velocity. That's acceleration. Acceleration is defined in 3 different ways. If something is speeding up, it's changing velocity. If it's slowing down, it's changing velocity. And thirdly, if it's changing direction, because velocity includes a direction, it's changing velocity as well. So acceleration is defined by speeding up, slowing down, and changing direction. The rate of change of velocity is acceleration. Number 4, the distance traveled divided by the time it takes to travel that specific distance. This is our calculation for average speed. You take into consideration the entire distance and the entire amount of time. It gives you average speed. You use this when you're calculating maybe the total distance that you have to travel and the total amount of time it takes you to get there, in terms of like a long road trip or a trip from one place to another that's going to take a long amount of time. Instantaneous speed is calculated the same way, time divided by speed, instantaneous speed is calculated the same way when it comes to distance divided by time, but it's in that exact instant, so it's a little bit different. Number 5, a measure of how hard it is to stop an object. How hard it is to bring something to a stop is momentum. It's kind of looked at as the opposite of inertia, because inertia is the object's ability to resist a change in position, so it doesn't want to move. Momentum is something that's moving, not wanting to stop. Again, number 5, a measure of how hard it is to stop an object, that is momentum. 6, speed plus direction, that's velocity. They're measured in the same way, but you're adding in a direction to what that object is traveling. 7, the amount of matter in an object is mass, and mass goes into a calculation on how you're going to get inertia, an object's ability to resist change in motion, and momentum, an object's ability to stop something. If something has more mass, both of those are usually increased. 8, speed of an object at one instant of time, that's instantaneous speed. Part B, our concept review, says circle the term that best completes the following statements. Number 1, the momentum of a falling leaf is greater than, less than, or equal to the momentum of a falling pine cone. Well, here you have to think about, if it's momentum, how hard it is to stop the object, and how much mass a leaf has in comparison to a pine cone. Which one is going to be easier to stop? Probably the leaf. So the momentum of the leaf is less than the momentum of the pine cone. Number 2, 2 objects have a mass of 70 kilograms. Their momentum is equal, changing, or unknown. Well, in this case, they have the same mass, that's equal, but momentum has to consider the movement of that object, how hard it is to stop the object. And because it doesn't tell us that the object is moving or not, you have to say that this is an unknown calculation. Number 3, when 2 pool balls collide and move away from each other, they eventually stop. This is because of momentum, friction, or inertia. Let's go back to our definitions. Momentum is how hard it is to stop an object. Well, if those pool balls are eventually rolling and they come to a stop, momentum is taking place. Inertia is how hard it is to get the object to move. Well, you hit the balls with the energy that you had with your cue stick and the other pool ball. It's obviously moving, but why does it come to a stop? It's because there's friction. There's this surface contact between the ball and the felt that's on the table, and because that contact is there, it slows the object down. In an ideal science world where there isn't any friction, if you hit something, it's just going to continue to move and move and move and move, but we obviously don't live in that ideal world. We got gravity pulling down, and we've got friction of that ball contacting the table. Number 4, a 50-kilogram object moves with a velocity of 10 meters per second. Its momentum is... Well, to calculate this, you're going to multiply the object's mass times its velocity to figure out its momentum. So 50 times 10 is going to give you 500 kilograms per meters squared. So it'd be this one right here, not 500 meters per second. It'd be 500 kilogram meters per second because you're factoring in the mass of the object that has a huge influence to an object's momentum. In the third portion, we've got directions to use this time and distance graph. The distance time graph below describes the motion of an object. Use its answer question 5 through 8. The first one says, over which interval is the velocity greatest? Well, velocity on a time versus distance graph is going to be anytime you have this upward motion. So the only two line segments that we have are AB and BC that have this upward motion. And the greater the slope, the steeper the line, the greater the velocity. So on this line right here, on number 5, you're going to write AB as a line segment. So just write AB with a little line over the top of it. Number 6, over which interval is the velocity 0? Now there's two different types of graphs we learn about in chapter 10, and the first one is our distance time graph. If we have a distance time graph in which distance is no longer increasing on the graph, it actually shows that that object isn't moving, which would tell you that the object doesn't have velocity in this case. The other one that we learned was a speed versus time graph, which showed the upward and downward movement, and if it's going at a constant velocity, it would level out. But this is showing no velocity at this time because distance isn't increasing. So over which interval is the velocity 0? You would say CD. 7, over which interval is the object accelerating? The object accelerating if it is speeding up or slowing down. So speeding up would be A to B, we got a change in velocity. B to C, we got a change in velocity. Those are increases in velocity. And D to E, it's actually slowing down its distance over time. And this one, so A to B, B to C, D to E. Number 8, what is the average velocity in meters per second from A to B? So here you're going to measure the distance and then the amount of time in that same distance and then divide. So from A to B, you've got a distance of 0 to 4. Looks like 4 meters, and that's in the time if I go down here to 3 seconds. So I've got 4 meters in 3 seconds. If I divide that, I get 1.3 meters per second. Number 9, use the space below to calculate the answer to the following questions. The velocity of an object goes from 4 meters per second to 12 meters per second in 4 seconds. What is its acceleration? If you remember back to lesson 1, our equation for acceleration is taking the final acceleration, subtracting it from the initial velocity, the final velocity from the initial velocity, finding the difference between those two, and then dividing by the amount of time that that change took place to find how fast an object is speeding up or slowing down. In this case, our final velocity is greater than, so we have a speeding up scenario. You take 12 minus 4, 12 minus 4 is 8, and you're going to divide by 4 seconds. 8 divided by 4 is going to give you 2 meters per second. It's speeding up at that rate. Number 10, a toy car moving at 3 meters per second collides and hooks up with a 9-gram toy car at rest, and they move together. What is their final velocity? Here you can refer to our measurement of momentum and our calculations of momentum, where you have the mass of an object and the speed of an object being added together because these objects are colliding and sticking together. So the math that you're going to calculate here is the first part, 600 grams in 3 meters per second. You're going to multiply those. 600 times 3 is going to be 1,800. It hooks up with a 900-gram toy car that is at rest. That means it's not moving. So you're going to take that 900-gram car and multiply by 0 because it doesn't have any momentum. It's not like you're trying to stop that object. And then you're going to try and compare this to the final velocity. Well, what we know is that the final velocity times the final mass equals the initial momentum. So in this case, we had 600 times 3 plus 900 times 0 adding all that up. Well, 900 times 0 is 0, so 600 times 3 is 1800, right? On the right-hand side of my equation then, for my calculation of final momentum, I have to add the total mass of these two objects together. So I have to add 600 plus 900. If I add those together, I get 1,500 grams, or 1,500 grams. Now, if I multiply by the velocity that I don't know, I have an equation that I can set up. So I know that on the left-hand side of my equation, I've got 1,800 equals 1,500 times the velocity. What I need to do is then divide 1,800 by 1,500 divided by 1,500 equals 1.2 meters per second. So imagine this. Your toy car is traveling at 3 meters per second, and it runs into another toy car, and because that second toy car is really heavy, it actually slows down and is now moving slower. Obviously, because of friction and gravity as well, it's going to eventually come to a stop, but as soon as that collision takes place, because the smaller car hit the bigger car, it slows the object down. Here you would write 1.2 meters per second as you calculated that final velocity with the law of conservation of momentum. Initial momentum versus final momentum to give us that overall law coming into play with our mathematical application. Hopefully that helps with the completion of Chapter 10 and reviewing all that we've learned in terms of motion, acceleration, and momentum. God's blessings.